Welcome back to our networking course. In this particular video, we shall be continuing from where we had stopped previously. So today, we shall be looking at IP addressing, we shall be looking at subnetting, and also we shall look at the basic networking commands that you can use in networking. So basically, IP addressing, IP stands for Internet Protocol. It's basically a unique number that we assign to every device, call it a node in a network. Each IP address identifies a device's host network and also its location on the network. So you realize this is an example of an IP address. So basically it helps us to identify a device that is within a network. Now IP addresses are basically logical addresses, that is to say they can change based on the location of the device. Every time I move from one network to another network and I connect, eventually the IP address of my device eventually changes. So it means it is logical, it changes based on the location. These addresses serve two primary functions. Number one, they help us to identify a device on the network and also to facilitate communication by routing data to the correct destination. So this is the major purpose of these IP addresses. However, they can be assigned manually or dynamically in our computer. For example, if I come to my computer down here under my network settings, okay, I come to my network and internet settings here, and then okay, right there, it's taking longer, I don't know why. I come to my change adapter options, right here. If I come to my maybe Ethernet 2 here, I can double click on it, and then under IP version 4, since we're working on IP version 4, you can double click on it, or you can just say properties, and then it will take you to your IP version 4 network settings. So when I double click on it, for example, I can be able to say obtain IP addresses automatically, and then it will give me, it will assign IP addresses to this computer automatically. However, if I don't prefer to use automatically, I can say use the following IP address, whereby I can assign an IP address to my device manually. So this is basically what I'm doing, maybe 1.5, and so it will give me a default subnet mask telling me the IP address you've given me here basically is a class C network, and that's why it is giving me a default subnet mask of 255.255.255.0. So basically this is a simple way you can assign IP addresses to your computer. Now let's leave that alone. Getting back to our document, we've seen that they can be assigned manually or dynamically. So IP addresses basically have two versions. We have what we call IP version 4 and IP version 6. So the two main versions that we have, IP version 4 basically has 32 bits in it. We shall see what we mean by that. And then IP version 6 basically has 128 bits. So this simply tells us IP version 6 is bigger, very, very big. So IP version 4 addresses are also represented in dotted decimal notation, or basically decimal notation. This is what IP version 4 address looks like. Then IP version 6 addresses, they are represented in hexadecimal notation, something just like this, with the semicolons appearing everywhere there. So this is hexadecimal notation. So remember, two devices on internet can never have the same IP addresses at the same time. It's only after the IP address has been freed that another client can be able to obtain that same IP address. However, if they are all connected on a network at the same time, they can never have the same IP address. Okay, now the different types of IP addresses, we have what we call the public addresses. These are basically used for communication over the public internet. We have what we call the private IP addresses, basically reserved for private use, used for communication within a local network. We have static IP addresses, for example, those that remain constant over time. Assuming you're going to assign an IP address to your printer, which is being shared by everyone, it means you must assign it a static IP address, such that it doesn't keep on changing, because if it changes, the next time I want to access the printer, I cannot access it. So it means you must use a static IP address. Then also we have what we call dynamic IP addresses. These are IP addresses that can change over time, which are often assigned by a DHCP server. Now these ones here, every time your devices receive an IP address, every time you connect on a network, if it has a DHCP server, you realize you obtain an IP address that has been assigned to you automatically, which may be able to be given to you if it has become free. It's now waiting to be assigned to anyone else. So benefits of IP addressing: they can help us in global communication, they can facilitate network management, they can enable resource access, and so on and so forth, which means they are very good for us to use them. Now, for this particular video, we're going to concentrate more into IP version 4. Now, we said IP version 4 basically is a 32-bit address. It basically has 4 octets. What I mean is, as you see, 128.11.3.31, each number here is representing an octet. This is an octet. Where the full stop is, you go to another octet, this another octet, this another octet. Now, this IP version 4 can also be represented in 2 notations. It can either be binary or decimal. For example, this 128 here is decimal. This 100 here is a representation of this 128, which is decimal. This 11 here is a representation of what you're seeing up here, which is binary. So this is decimal here, and this 3 here is decimal, and this upper one here is binary, a representation of the 3 down here. Probably you wonder how do these come about. We're going to do it just in a few minutes. The 31 here is a representation of this decimal, of this binary number you see up here. So each octet, assuming this is an octet, which we are seeing here, 128 here, which is an octet, each octet ranges between 0 to 255. Whichever value is going to be within this octet must range between 0 to 255. Okay. So let's try to see how do we convert from decimal to binary and from binary to decimal. We have a simple illustration here, though we don't know how this came about. We want to see how indeed it can come about. So let's go down to our table here. Now we're going to convert, first of all, this value we're seeing here into decimal. This is in binary. We want to convert it to decimal. So what we're going to do, we're going to write these values here. 1, we have another value is 0, another value is 1, another is 1, another is 0, and then the rest are 1, 1, 1, and 1. So these are the 8 values that we have in an octet, because an octet basically has, this is a binary version of a certain value that we're going to have in our network. So how do we convert this to decimal? We're simply going to say, converting this to decimal, we're simply going to expand this. So since it is in byte base 2, we're going to expand it in this manner. We're going to say 1 times, we can use this x for a times, 1 times 2. Basically, here we're having 1. Okay, let me first copy this from here. Let's begin from this side. 1 times 2. This 1 here times 2, which is the base of the number. But this base should be raised to the place value of this given number. Here, this place value is to the power 0. Maybe let me raise that. Raising it, we use this value here to the power 0. So this is 1 times 2 to power 0. Now maybe I can just copy this, so that we don't struggle writing it everywhere. Let me try to write it everywhere here in that manner. Now, this value we've copied here was basically for this particular place value where this 1 is. This is 1 times 2 to power 0. However, for this one here, it is 1 times 2 to power 1. Instead of having 0 here, this will be 1, because the place value for this is 1. This is 0, this is 1. So then this will be 1 times 2 to the power 2. The place value for this is 2. This is 0, this is 1, this is 2. Then now this one is 0, not 1. It is now 0 times 2. This one shall write here as 0 times 2 to the power 3, because we're raising to the power from zeros, from place value of zeros, 1, 2, until move upward. Now this one is 1 times 2, but then guess what? This will be to the power 4. And then this will be 1 times 2 to the power 5. Here we have a 0, so this will be 0, not 1, but 0 times 2 to the power 6. We're converting this. So then finally we're going to have this as 1 times 2 to the power 7. So we have expanded the meaning of this. We have expanded this in this manner. So now simply we're going to say any number to power 0. This is our reference table that's going to help us to understand what do these things mean. So 2 to power 0 is basically 1. So 1 times 1 will give us 1. Okay, let me put this maybe in another color so that we can be able to follow it clearly. Purple. No, purple is not clear. Red. Is red okay? Okay, that's red. So 1 times 2 to power 0 is 1. So 1 times 2 to power 0, which is 1 times 1, will give us 1. We'll come here. 1 times 2 to power 1. 2 to power 1 is the same as 2. So 1 times 2 will give us 2. 1 times 2 to power 2, which is 2 to power 2, will give us 4. Here, 0 times 2 to power 3. 2 to power 3 is 8, but 8 times 0 will give us 0. 1 times 2 to power 4 is the same as 16. 1 times 2 to power 5 is the same as 32. 0 times 2 to power 6, 2 to power 6 is 64, but times 0 will give us 0. And then finally you have 1 times 2 to power 7, which is the same as 128. So then we add up this value here by saying 128 plus 32 plus 16 plus this is 6 plus 1, which is 7, plus 7 will give us 183. So it means by converting this binary number here, these values here, into decimal, we get the value of 183. So we have converted this to decimal. So you can as well have another number. All you have to do is expand it right from your left moving towards your right from your right moving towards your left. So basically this is how we can convert a number like this one into decimal. Now let's look at how we can convert a number which is in base 10, like now this one, which is decimal, into binary. At least we have seen this example of how we can convert from binary to decimal. But now here we're going to convert from decimal into binary. So what we do here, we are going, or what happens here this time around, this value here, we shall keep dividing it by the value to which we're converting it. For example, we want to convert this into base 2. So we're going to divide this value here by 2. So 27 divided by 2, we get 13. When we divide it by 13, 13 by 2 will give us 26, and so we have a remainder of 1. Okay? Then again we'll continue. 13 divided by 2, we get 6. 6 times 2 is 12. We have a remainder of 1. We'll continue again. 6 divided by 2, we get 3. 3 times 2 is 6, remainder 0. We divide again by 2. 3 divided by 2, we get 1. 1 times 2 is 2, remainder 1. Of course, now we can't divide 1 by 2. We can't divide by 1 by 2. So because of this, we are going to write our value from down moving upwards. So in this case, we're going to have these values in this manner. Let me try to list it here. It means we're going to have let me first write it behind here so that we can be able to. Okay, let me first write it here. So here, our first value down here is 1, then another 1 follows, was this one here. Then if I come to this one, we're writing from down going upwards. 1 1 0 1 1. So now you realize this is a representation of 27 in binary. However, since we work with octets that have 8 bits, IPv4 which has 8 bits, the other values we're going to add here will basically be zeros, but we'll add them on the other side, because if we add them here, it means this one here will be to the power, a higher power. So 1 2 3 4 5 6 7, another 0 is missing here. So this is basically what we have as 27 in binary. So assuming it was another number, you can still convert the same and you get the same value. Maybe we can as well repeat what we have just done here, which was 183. Let me see, 183. So what will this give us? I don't know whether it will give us the same value. Let me see. Remove this. So we're having 183 right here. So we say 183 divided by 2, we get 91. So you have 2, you get 91. 91 times 2, 91 times 2 will give us 182. So which means we have a remainder of 1. Divided by 2. 91 divided by 2, we have 45. Okay? 45 for 90. 90, we have a remainder of 1. 45 divided by 2, we have 20, 24. 24, 22. 22 divided by 22 by 2, you get 44, so we have a remainder of 1. Then 22 divided by 2, we have 11. But this time around, 11, we have a remainder of 0. By 2, we have here 11 divided by 2, we have 5 for 10. Okay, 5 for 10, remainder 1. Then again by 2, we have here 5 divided by 2, we have 2 for 4, remainder 1. Then finally, we divide again by 2. 2 divided by 2, you get 1. And so when you divide by 1, you get 1, remainder 0. So it means our value here, where is it rushed up? Our value here, which is 183, will be the same as writing 1 from down going upwards. 1 2 3 4 5 6 7 8. So it means we're going to say 1 followed by 0 followed by 1 1 followed by 0 followed by 1 1 1. So this is a representation of 183, which is decimal into binary. So I hope this has been clearly understood. Okay, let's go back to our document. So we have seen how we can convert decimal to binary and from binary to decimal. Now let's continue. This is done. Let's look at IPv4 divisions. So basically, an IPv4 network like this is divided into two. It's divided into what we call the network portion or the network ID, and then we also have the other part which we're calling the host ID. So basically, the network ID will help us to identify the network, and the host ID will help us to identify. Okay, so we're basically saying that an IPv4 network basically has two divisions. We have what we call the network ID and also the host ID. Usually, the network ID helps us to identify the network, and then the host ID helps us to identify the hosts or the clients that can be given the IP address. So basically, if it's a class A network, usually the first octet is always reserved for is always what we use to identify the network bits of that given class. So it means the class A network, 8 bits are reserved for the network bits, and then the remaining 24 bits, because remember each octet has 8 bits, the remaining 24 bits are basically for the hosts. If it's a class B network, the 2 the first two octets are basically for the network, and then the last two are for the host. Suppose it's a class C network, it means 3 octets, the first 3 octets are reserved for the network, and then only 1 octet is reserved for the what? For the host. So this is basically what we shall be handling in this video. Now, we see that class A networks are very huge networks. It means, remember, if only 1 octet is for the network, and then the remaining are for the host, which means it has so many number of hosts that can be created in that given network. Class B has slightly fewer, and Class C has slightly fewer, because all the 3 octets are for the network, and only 1 octet is reserved for the host. So which means we can only have few clients with a Class C network. So usually, Class A networks are reserved for the governments and large organizations. They use always this Class A network, and then Class B is for medium companies, and Class C for small companies, and so on and so forth. Now we also have Class D, which is basically reserved for multicasting, and Class E is reserved for experimental purposes or basically research. So other special addresses, we have what we call the loopback addresses. Now this one, 127.0.0.1, they're basically addresses that are used for to direct traffic to ourselves or to yourself if you're using it in a network. Then we have what we call the link local addresses. This is if you're using packet tracer, you find that this is always defined as a PIPA. So you find these addresses are basically assigned automatically to our devices. Then you have also these other testnet addresses, which are basically used for learning purposes and so on and so forth. Now, let's look at subnet mask. Basically, in our given network, a subnet mask is basically a 32-bit number that divides an IP address into network and host portions. It helps devices determine whether an IP address is on the same local network. For example, if you have a subnet mask of 255, here we have default subnet masks for different classes. Slash 255.0.0.0 can also be represented as /8, meaning you have 8 network bits which are reserved for that network, and then the rest are for the host. So this 255 is also a representation as /16, and then 255 is a representation of /24. So this we shall see how it is clearly applicable. Now let's look at subnetting as we continue. Now, under this, we shall try to understand what is subnetting, how do you create a subnet, how do you find a host and a network ID, how do you find a subnet mask of any given IP address. So let's see how this is possible. First of all, subnetting is a process of dividing a large network into multiple smaller networks. We divide a large network into multiple small networks. First, for instance, you may be given a network as this, 192.168.10.0.0/26. This network is very huge. It is so huge. We can divide it to create other smaller networks within this, with this given IP address. So, as we do that, there's something we call the CIDR value, which is the classless interdomain routing. This one basically gives us the total number of network bits in a subnet, only the network bits. Therefore, an example would be, as a network administrator, you may be required to create 4 subnets, 3 subnets, 5 subnets, 100 subnets for a school that has 4 departments. Here you're creating 4 subnets or 4 networks for a school that has 4 departments. For example, it has an IT department, admin block, finance, and student labs. Suppose the company uses a Class C IP address. Without subnetting, all computers would work in a single large network as seen below. You'd find that if you don't subnet this network, all the computers would continuously work in one given subnet or one given network. A single network, which would be something like this, from 1 up to 254, for example. However, if we divide this network into subnets as required, after which computers will receive only the broadcasts that belong to them. So, since the company has 4 divisions, it can divide its network into 4 subnets or 4 networks. The following figure will show the same network after subnetting. For example, after subnetting that network which was single behind there, you can have one side, this is one network, which is 1 up to maybe 62, another network from 65 to that, another network is here, another network is this. So this is possible because of subnetting. Now, how do we subnet? First of all, before we subnet, we shall need to find certain values or certain things that will help us to subnet a given network. For example, given an IP address, they can tell you, you'll first of all need to find the number of networks that can be created in that given network. For example, to find the number of networks, we use the formula 2 to the power n, in this case where the n represents the number of borrowed bits from the host. Okay? If you have borrowed bits from the host, if you look at the host, is there anything you borrowed from the host? Then whichever value you've borrowed from the host, you raise it to the power of 2 to the power that number. So that will give you the number of networks in that given IP address. So also, to find the number of IP addresses on each network, we shall also use the same formula 2 to the power n. By this time around, the n is the total number of host bits remaining, or what we call the remaining bits, and that will also be able to help us to find that. Now, to find the number of hosts in each network, this is basically a total number which was given here, but now here to find the number of hosts in each network, we shall say 2 to the power n minus 2, where this is 2 to the power the remaining bits minus 2, which will give us that number. However, we subtract minus 2 because on each network, the first IP address is always reserved for the network ID, and the last IP address is always reserved for the broadcast ID. So because of that, we always subtract minus 2. Now, let's go ahead and look at some examples. Let's try to subnet this number here, 5.0. We shall look at this example, look at this other example, and then this example here. We see what's changing here is basically the subnet mask behind here. Okay, so let's try that. Right here, we have our first example is 5/24. Now, first of all, we said that we shall need to find out the meaning of this /24 here. This /24 simply means we have 24 network bits. Remember, we said that the CRD value basically describes to us the network bits that are found in that given IP address. So now this one here has /24, which means we have 24 network bits. How do we represent them? On our 4 octets that we have in our network, we're going to represent them in this manner: 1, 2, 3, 4, 5, 6, 7, 8, because each octet basically can accept 8 bits. So the next one will be 1, 2, 3, 4, 5, 6, 7, 8. Those are now 16. The next one will be 1, 2, 3, 4, 5, 6, 7, 8. Those are 24. So how about now the rest? Because a network ID should be able to have 32 bits. So the rest will be zeros because the network bits are only 24, and so the host bits will only be 8, and there will be zeros. 1, 2, 3, 4, 5, 6, 7, 8. So now here we have our representation of these 24 network bits, which is these first 3 octets, and then the remaining ones are the host bits. So now, given this IP address here, how many networks can be created in this network here, in this IP address here? How many networks can be created here? How do we do that? How do we find that? We're told that the number of networks in a given IP address is given by the formula 2 to the power n, where n is the number of the borrowed bits. Now you look at this. Here, this network here, the /24 ends here, and you realize that there is nothing that borrowed from this host part, because remember, in a class C network, the last octet is always reserved for the host. But then, /24 only ends here, so which means there is nothing that borrowed from the host bits, which means you can say it is 2 to the power 0. So which means they have only borrowed 0 from this other side, which means 2 to the power 0 would give us 1. Any number to the power 0 is 1. So you realize that also in our reference table here, /24 simply means you can only create one subnet, or you can only create one network. And so we have proven it that indeed a /24 has only given us one network, because there's nothing that was borrowed from this side. So having done that, we'll go to the next thing. How do we find the number of IP addresses in this given network? How do we find the number of IP addresses in this given network? Now, this number of IP addresses will basically be the total number of all IP addresses that can be created in that given network. So we shall use the formula 2 to the power n, but this time around, the n is the number of the remaining bits. What do we mean by remaining bits? Having borrowed the bits from this other side, how many are remaining? Here we borrowed 0, which was this. So having borrowed 0, how many are remaining? We're remaining with 8 of them. So which means we're going to have 2 to the power 8. This should give us around 256 IP addresses, which means with that given network there, we can create at least 250, we can have at least 256 IP addresses in that network. However, this number of IP addresses here is the total number of all IP addresses in that given network. So then, how do we find the number of hosts, or the number of usable IP addresses, or the range of IP addresses in that given network? Here, we find that by saying the total number of IP addresses we have in the whole network minus 2. So which means if we have 256 as the total number of IP addresses minus 2, this should give us 254. So now, why did we subtract minus 2? Because we said that one IP address is reserved for the network ID and another is reserved for the broadcast ID. So because of this, we have to subtract minus 2. So our IP address was saying, was having this this was the value that we had for our IP address, 192.168.5.0. So now, how do we find? So we've realized, first of all, we've realized that this network here can only create one IP address, which is going to be only one. So we can say network. We can just say use n for representation of network. So we can only create one network with this. So how do we get the network ID for this given network? All we have to do is to copy this IP address here and we paste it down there. So we just paste it here. Now, what is happening here is to determine the network ID for this given network, it means we shall look at this last octet here, because remember, this is a class C network, so the first 3 values for them, they remain constant, they don't change. So what is going to change is only the values for the last octet. So because of that, we shall say if all the values in this octet here are turned off, if all these zeros here are turned off, assuming these were basically ones here and they were turned off, it means you would get 0. Where these ones are all turned on here, this will give us 255. So suppose all these values are turned off, we shall be able to get 0. Or simply, you'll just copy the original value that you have here. This will eventually be the network ID for that given network. So suppose all of them are turned off, we have 5.0. So having gotten this value, let's see how we can find the broadcast ID. If to find the network ID, we said all the values here must be turned off and we got 0, then the broadcast ID will be the opposite of that. It will be all the values here turned on. If they are all turned on, then we shall have 255, because by converting this value, these ones here, which are here, into decimal, we get 255, which means they are all turned on. We have 255. So down here, we shall have 255 as a broadcast ID. Then, having done so, how do we find the usable IP addresses in this given network? We said that the usable IP addresses in this network will range between 192.168.5.0 up to 192.168.5.255, which means the values will range between 0 and 255. So which means we shall have 192.168.5.1, because from 0 you go to 1, up to 192.168.5.254 because you're going to run from 1, 2, 3, 4, 5, 6 up to 254, and that's where you're going to stop. So all these are reserved for our clients. From 1, 2, 3 until 254, these ones are basically to be used by our clients. So this is basically how we subnet. So this is a simple illustration of that, how that is done. Now, we have another example, this time around, which has a /25 here. And so this is maybe 2 to the power 7, assuming that is 2 to the power 7, with a /25. The previous one had /24, which means it had 24 network bits. But now, if we have 25, /25 simply means we have 25 network bits. And so that will mean you're going to have all these. Oh, what have I done? We have 1, 2, 3, 4, 5, 6, 7, 8 for the first octet. Then you have 1, 2, 3, 4, 5, 6, 7, 8 for the second octet. Then you have 1, 2, 3, 4, 5, 6, 7, 8 for the third octet. When you add up these 3 octets, we already have 24 network bits. But we are told we are having 25 network bits. So where shall we get the other 1 bit to add to get the 25 network bits? It means we're going to borrow it from this side. So instead of having all this one is going to change into 1. So which means now we have 25 network bits. So now, how do we find the number of networks that can be created in this given IP address? We say it's given by the formula 2 to the power n, where n is the number of borrowed bits. How many bits did you borrow? We borrowed 1 from this other octet here to add into our network bits. So because of that, we say 2 to the power 1. And 2 to the power 1 will give us 2. So which means we, with this /25 network subnet, we can be able to create at least 2 networks or 2 subnets. It agrees with what we have in our reference table here, where it says /25 can give us basically 2 subnets. So that is very true. Then, how do we find the number of addresses, the total number of IP addresses in this given network? The network bit and network ID and broadcast ID inclusive. How do we find that? We shall say 2 to the power n, where n is the number of the remaining bits. Since we borrowed 1 bit from the last octet of this network, that means of the 8, we shall remain with 7. We borrowed 1, and so there are 7 bits remaining. So this will be 2 to the power 7. So 2 to the power 7 will give us a total of 128 IP addresses. So the total number of IP addresses in each network will basically be 128. So this is network ID and the broadcast ID inclusive. Therefore, how do we find the number of hosts or the usable IP addresses? It is the total number of IP addresses minus 2, which is 128 minus 2, which will give us basically 126. So these are the IP addresses that will be given basically to our clients. Therefore, getting back to our network here, it means this time around, instead of having this, we're going to have network 1, we're going to have network 2, we're going to have 2 networks. Hey, we want to have network 2. I was almost writing more. So since we created only 2 networks, we're going to have 2 networks. So we shall copy now these first 3, because we realize this is a class C network. The first 3 values are constant. So we said to get a network ID, we shall copy that and first write that like that. Then we shall say if all the bits are turned off, it means we shall get 0. So by getting this, by having that value, we have our first network ID for our first network, which is right here. Now, how do we get the network ID for the second network? What we shall do to get the network ID for the second network, we shall only have to add the total number of IP addresses to the network ID 1. What do I mean by that? We shall first write the first value, which is that, and then we say 0 plus 128 should be able to give us the network ID of the second network. So this will give us 128 there. So having gotten this, how do we determine the broadcast ID? The broadcast ID for network 1 will basically be 128 minus 1. It will be less by 1 of network 2. So which means we shall write here the constant things, first of all, constant things, and then we shall say, instead of having 128 here, we shall have 127, because to get the network ID for network 1 will simply be the network ID for network 2 minus 1, which will give us 127. Therefore, how do we get the network ID for network 2? How do we get the broadcast ID for network 2? The broadcast ID for network 2 will simply be, since it is the last network within this given IP address, since it's the last network, it means it will be the last broadcast IP address of that whole general network. So what we do here is, we shall say, if we said that here all these were turned off, suppose now all these are turned on, it means we shall have 255. If all these are turned on, we have 255. If all these are turned off, we have 0. So by having this, by doing this, we have now the network IDs and the broadcast IDs. Now, how do we find the usable host? It means we just look at what is between 0 here for network 1 and 127, and also what is between 128 and 255 for network 2. So it means here we shall have 7.1 up to 7.126, because the last broadcast ID for network 1 is 127, so we can't have anything beyond that. So it means 126 will be the last usable IP address given to our client, and 1 will be the first usable IP address given to our client in network 1. So in network 2, we shall again copy that, and then this will be, since the network ID is 128, so which means the first IP address to be given to our client will be 129, because 128 you go to 129, and then the last one will basically be 254, because we can't exceed 255. So all these, so in network 1, these are the network ID, broadcast ID, and the usable IP addresses, and network 2, we have this. So these ones we give to our clients for use. Let's finalize with the last example. I hope this is now getting easier. In the last example, we have a /26, and here we can use 10 here this time around. 192.168.10.0/26. /26 simply means we have 26 network bits, and so that will mean you have the first 8 here, you have the first 8 here, you have the first 8 here, giving us 24. Now if you have 24 here, where are we going to get the next 2 to make 26? It means we're going to borrow it from the last octet. So 24, 25, 26, 27, 28, 29, 30, 31, 32. So it means now we have 26 network bits already represented in our table. Now, how do we find the number of networks or subnets in this given network? We shall use the formula 2 to the power n, where n is the number of the borrowed bits. How many bits have we borrowed from here? We have borrowed 2 bits from the last octet to add onto our network. So we have borrowed 2. So by borrowing 2, we have 2 to the power 2, which will give us basically 4 subnets. So now this is the number of networks or subnets that can be created in this given network. It agrees with what we have here in our reference table, whereby /26 will basically give us how many networks? 4 of them. So we expect to have 4 networks in this kind of number. So now, how do we find the number of IP addresses? The total number of IP addresses in this given network, it will also be 2 to the power n, where n is the number of the remaining bits. Having borrowed 2 in this octet, how many are remaining? We're remaining with 6. So this will be 2 to the power 6. And 2 to the power 6 will eventually give us 64 IP addresses, which means in each and every network we shall have basically 64 IP addresses. Therefore, how do we find the number of hosts or usable IP addresses? It is basically 64 minus 2. 64 minus 2, which will basically give us 62. So basically we shall have 62 usable IP addresses in each and every given network. So now we go ahead and we'll create those networks. So we have 4 networks. This will be network 3, and then we have network 4. Now, how do you determine the network ID for the first network? All you have to do is to copy what is here, or I can just copy these first 3 octets, which are constant, and we paste it here. Then we say, if all the bits are turned off, we shall have 0. So eventually that gives us the network ID of that given network. So with that one already found, we can find out the rest. So first of all, we shall need to find also the network ID for the second network. And we said, to find the network ID for the second network, we shall have to add the total number of IP addresses in that given network onto network 1. So we shall say, we first write that, and then we shall say 0 plus the total number, which is 64. This will give us 64 IP addresses, because we said in each and every network we shall have 64 IP addresses. However, in that network we shall have 62 usable IP addresses. So by going to the third, all you have to say is 64 plus 64, which will give us 128. And then going to the fourth, we shall have 128 plus 64, which will give us 192. So which means we already now have all the network IDs for all the networks. Now, how do we find the broadcast ID? We said to find the broadcast ID for network 1, we subtract network 2 minus 1. So it means we shall first write that, which is constant, and then we say 64 minus 1, which will give us 63. So this becomes the broadcast ID for network 1. So to find for network 2, we shall subtract network 3 minus 1. So which means we shall have that dot 127. So that becomes the broadcast ID for network 2. Then to find for network 3, we shall subtract network 4 minus 1, which means we shall do that dot 191. Then finally, to find the broadcast ID for the last network, N4 being the last network, it means you're going to say, if all these are turned on, it means that should give us the value for the last broadcast IP address, which is that dot 255, because if these are all turned on, you have 255. Now to find the usable IP addresses, just a matter of writing that, and you say from 0 you go to 1, and then the last one in that network 1 will be that dot 62. So because within this network from 0 to 62, from 1 to 62, those are the ones we give to our clients in network 1. So in network 2, we're going to have that, and since it is the network 64 is the network ID, so it means the first usable IP address will be 65, and the last usable IP address will be 126. So that will be the last usable IP addresses in the given network. Then now for network 3, we shall copy that and say, since network ID is 128, the first usable IP address in network 3 will be 129. Okay, let me try to reduce this so that you can see very well. Okay, something like that will be 129, and then the last IP address in that given network will be 190, which we have there. Okay, so this is quite amazing. So then for this one, for the last network, we shall copy that and say, since the network ID for network 4 is 192, so which means the next network ID, the first usable IP address will be 193, until finally the last one will be that one dot 254. So by doing this, we have all our networks handled. So now right here you can see we have network 1, its network ID, broadcast ID, and the usable IP addressing. So this is all you need to know about subnetting. So finally, let's also handle some basic networking commands that we access, that we use in networking. We have what we call ipconfig, we have ipconfig all, we have what we call ping and nslookup, and also tracehat, plus others. You'll find them out at your own time. So the ipconfig basically displays the current IP configuration of a network adapter. It displays the current IP configuration. It provides information such as the IP version 4, the subnet mask, and default gateway. And this is useful for quick identifying of your network. So if you write ipconfig, let me try to do that using my command line. If I say ipconfig and say enter, oh, it seems I'm not connected on any network right now, but that should not worry us. So basically, if I was connected to some network, let me see, why am I not connected on any network? Okay, so basically all you have to do is to press ipconfig, and just to give you those different informations that we need here. So for example, here we have IP version 4, which is given here. This was the last time I did that, and so it gave me this IP version 4. And also here we have the default gateway, which is often the IP address for your router. And then we have a default subnet mask here, which is a class C default subnet mask. And so then up here we have the IP version 6 IP address. We saw that here it is hexadecimal, so it's quite a huge thing. So these ones are basically how we can do ipconfig. Now, if you do ipconfig all on your command line, saying ipconfig all, this should be able to give us an extended version of the ipconfig that provides more detailed information about the DHCP network configuration. It will give us the MAC address, it will give us the DHCP status, it will give us the DNS server information, and all that kind of stuff. And so right here, by pressing ipconfig all, this is the information it gave us. So we're able to access, I have the MAC address down here, where the physical address here is. We're able to see other information that initially were not displayed there. So now we have them in this section. Then also, we look at the ping command. Basically, the ping command is used to test network connectivity to a remote host. And so, suppose you want to check whether there's connectivity to a given device, you can say ping. And so when you pinged this, for example, I was able to get this feedback, which was an indication that indeed there was a positive feedback in this. On this other side, I tried also to ping this given IP address, and so there was a failure on this case, which was basically 100% loss. So a pinging is basically a command we can use to determine whether a given host is basically reachable. Now let's look at this other final one. nslookup is basically called a name server lookup. This command is used to query the domain name of a given IP address. So basically, assuming you have an IP address like this one here, and you want to query it, you can basically say nslookup that given domain. And so it will tell you, oh, this domain here uses this particular IP address. So that's basically what nslookup is all about. It can resolve a host name to an IP address or an IP address to a host name. It helps us to find out the owners of certain given domains and also certain given IP addresses. Then tracehat, or what we call the trace route, basically traces the route that packets take to reach a given destination on a given network. So it shows the sequence of routers, or what we call the hops, that a packet can traverse along with the time it takes to reach that given network. So here, when I try to trace route this domain here, it was able to take all this time. It took around 220 milliseconds to finish up with the trace with the route. And so these are the different hops or the different routers it was able to access until finally it completed it. So basically, that's all we need to know about the basic commands of networking. And till then, we're yet to complete, to continue with other studies. Thanks for watching for today. Bye-bye.